Thank you, Sagar. And also I'd like to thank all the organizers. So I thought that since this is a theoretical sciences department, I'll start with a math question which will sort of pop up in the paper. So maybe I'll just take a couple of minutes to write the question. So I don't know the answer to this question. It's still something which I'm trying to figure out, and it pops out in this paper. So anyways, so I'll be talking about stable mixing in Hogdog games under best experience payoff dynamics. This is joint work with Yuval Heller from Bar-Ilan University in Israel. So Hogdog game is something which you've already encountered. An economic example for this sort of a situation could be where you have a buyer and seller. A seller is planning to sell a house, and roughly, let's say that there are two bargaining strategies. You can either be an aggressive or a hawkish player, or you can be a flexible DAO. The story here is that if you have two DAOs, then they both trade with a fair price. If you have two hawks, they are both aggressive, they fight, and the bargaining is likely to fail, which means that they both end up at a low payoff. If there is a hawk and a DAO, then a trade occurs with a price which is favorable to the person who is more aggressive. This story can be roughly represented in this payoff matrix. The payoff matrix which you will usually see for a hawk-dove game would be slightly different. It will have different parameters, but essentially this game captures everything. As you can see here, this game sort of has three Nash equilibria. One Nash equilibria is where player 1 is choosing to be aggressive, player 2 is choosing to be flexible or a DAO. That's one Nash equilibrium. The second one is where player 1, the buyer, is flexible and the seller is aggressive. And then there is also a mixed Nash equilibrium which you saw earlier. And one thing which I would want to point out is that in the earlier talk, I think in the morning talk, when the Hogdove game was mentioned, it was mainly in a single population setting. The setting which I would be studying has two populations. So that's something which I'll get into as when I introduce the model. So this game has been studied in various economic applications. I'll not get into any of these applications, so I'll just directly go to the question which we are trying to answer in this paper. So as I said, this game has three Nash equilibria, and qualitatively you have two distinct kind of equilibrium. One is where you have a boundary equilibrium, the pure equilibrium, in which one player is choosing to play one sort of an action. It's a pure action, there's no mixing. And the other player is also similarly not mixing. So these are the pure equilibria. Those would correspond to H1D2 and D1H2. And then there is also an interior equilibrium where the players are mixing. And the question naturally is, if you have multiple equilibria, the question is which outcome is more likely to arise. And the answer to this question would obviously depend on the kind of model you're going to write. If you write down a one population model and look at many evolutionary dynamics, then that will give you one sort of a prediction. If you're looking at a two population version of it, which we are doing in this paper, it will sort of give you a different sort of an answer. So what we are going to do in this paper is study the hog-dove game in the two population dynamics case. Earlier results in the literature sort of suggest that under many evolutionary dynamics, so I did not specify the dynamics, but the many sort of includes the most commonly studied replicator dynamics and also other dynamics which are sort of related to best response dynamics. The earlier results kind of show that only the pure equilibria are going to be stable, meaning that if you have two populations, one population, agents in one of the population are all going to choose a hawkish action, and all agents in the second population are going to choose the dovish action under many evolutionary dynamics. What we show in our paper is that something in the interior can be stable if we study a certain evolutionary dynamic, which is called as a best experience payoff dynamic. So what I'll do later is I'll try to introduce the best experience payoff dynamics and try to argue that this dynamic is a reasonable sort of a dynamic. The model which we'll consider, it's very similar, but now we sort of, in the paper, we will also sort of allow for some sort of asymmetry. You can have L to depend on the population. So L here could be L1 and G could be G1 and all sort of things. But for the points which I'm going to make, that is not going to be very important. So let's just say that this is L and this is G. And again, this will have two pure equilibria and one mixed equilibrium. The story now is that there are two populations. Population 1 has a mass of size 1. Similarly, population 2 has a mass of agents of size 1. We have agents in population 1 who are randomly matched with agents in population 2. And when they are matched, they play this hog-dove game. Now, when we consider a two population model, in order to write down the population state, you will need two numbers. If you have a population under the one population dynamics, you only need one number. But here, you'll be needing two numbers. So pictorially, if you're studying the one population dynamics, the dynamics are going to be on a line. If you are studying a two population dynamics model, the population state would be lying on a square. So now here the population state P1 would represent the share of agents who are playing the hawkish action in population I. So for example, if I consider the population state like this, so this state would correspond to a place where all agents in population 1 are playing the dovish action, and half of the agents in population 2 play the hawkish action, and the remaining half play the dovish action. We assume that some agents die and new agents are entering the population. A new agent who enters the population plays according to this particular function. Here you have this state space, which means that there are two numbers which represents the population state, and the population state evolves according to this. So let me try to explain what this is. So let's look at the first equation, the right-hand side. W1 represents the probability that the new agent who enters the population plays the hawkish action when the population state is P of t. And then P1t is the probability that the agent who leaves the population is the hawkish guy. So this sort of represents the net rate of change of agents who play the hawkish action in population 1. And similarly for the agents in population 2. Now, the goal is to characterize the limit points of these dynamics. So what we do is we run these dynamics and then see firstly whether this converges, and if it converges, does it converge to a Nash equilibrium or not. And clearly, the function which I have here, it will depend on the sort of dynamic which I'm going to study. Great, some standard definitions, so I'll just quickly go through these definitions. P star is said to be a stationary state if it is a rest point of these dynamics. And a stationary state is said to be Lyapunov stable if a population, if it starts near it, and it has to stay close to it. If it is not Lyapunov stable, then it is said to be unstable. And then we say that a state is asymptotically stable if it is Lyapunov stable, and also that if you need to be able to find a neighborhood such that if you start in that neighborhood, you get to P star. And then we call P star, the set P star, to be globally stable if the population converges to this set starting from any initial interior state. So that is a lot of words. So I'll try to illustrate this, these evolutionary dynamics using a very well-known dynamic called as the best response dynamics. So here the setting is that the new agent who enters the population, the assumption is that the new agent knows the population state and also knows the payoff matrix which is being played. So just to keep everything simple, let's say that this is the payoff matrix given. A new agent enters the population, knows the population state, also knows the payoff matrix which is being played. And then the assumption is that this new agent chooses a myopic best response. So here, in this setting, I am a new agent who enters population 1. If I know the population state, I can do some expected payoff computations. If I play H1, with probability P2, I'll be encountering someone playing H2. And with probability 1 minus P2, I'll be encountering someone who's playing D2. So that gives me a total payoff of 0 and then 1 minus P2 times 1 plus G. Similarly, if I compute the payoff of playing D1, I'd be getting 1 minus G with probability P2 and then 1 with probability 1 minus P2. So now there's a typo here. This should be H1 is preferred to D1 as long as the payoff I have here is greater than the payoff I have here. So as long as P2 is smaller than G, H1 is something which I would pick. These would be the best response dynamics for agents in population 1. And again, when you are exactly at P2 equal to G, there is sort of a discontinuity. I'll not get into the technical details. You can just assume that here the population is not changing. P1 dot is just 0. So as you can see, the state space is now a square. What we've done is we've divided the state space. These are the places where P1 dot is less than 0. These are the states where P1 dot is greater than 0. We can do a very similar analysis for agents in population 2, and this is what we would get. And if we combine these two things, we sort of get the phase portrait. And this phase portrait sort of intuitively tells you why only the pure equilibria are going to be stable under the evolutionary dynamics. So let me try to explain the phase portrait here. So what these arrows sort of show is the direction of flow. So for example, let's say I'm starting in this particular region. Here, P1 dot and P2 dot are both going to be less than 0. And then it sort of moves in this direction. And then once it enters this region, P1 dot is less than 0 and P2 dot is positive. So it kind of moves in this direction. And then it hits, it reaches this particular state. And then similarly, you have, if you're starting somewhere over here, you would move in this direction and then eventually converge to this particular state. And notice that this particular hollow dot here, that sort of represents the mixed Nash equilibrium. As you can see, it is not stable. It's not stable because, so let's say you're starting exactly at that point, you sort of remain there, but even if there is a slightest bit of perturbation, what happens is that you would either go here or you would go down here. So that's why only the boundary equilibria are going to be stable under the best response dynamics. Now we'll consider the best experienced payoff dynamics. And now the story is that a new agent who enters the population, we are making an extreme assumption here. Earlier we said that the new agent who enters the population knows both the underlying game which is being played and also the population state which is there. Now the assumption is that the new agent who enters the population does not know the true population state, and also does not know the payoff matrix, does not know the underlying game. All the agent knows is the set of available actions, set of actions available. So what the agent does is that tries each of the actions k times, few times, and then chooses the action which has given him or her the highest payoff during the testing phase. This kind of dynamic was sort of introduced way back in the late 90s, and then the corresponding dynamics were studied sort of recently by my advisor and some co-authors. Okay, so now we'll try to get to this equation. So great. So now I am a new agent. Let's say I'm a new agent in population 1. So when I try out the H1 sample, when I try H1, I'll be getting a certain number of hawks from the population 2 and a certain number of doves from population 2. And these samples, which I'm going to get, are going to depend on the population state. In particular, when the population state is P1, P2, this xk pt will be the number of hawk players in my H1 sample. And similarly, yk will be the number of, sorry, again there is a typo. I fixed the typo, but I guess the slides which were here did not fix it. But anyways, this is the number of D2 players in the D1 sample. Anyways, okay. So now playing H1 would give me 0 when I encounter someone who is playing hawk, and it will give me a payoff of 1 plus g when I encounter someone playing the dovish action. Since xk is the number of H1 players in the sample, the number of dove players in the sample is going to be k minus x. So this is the payoff playing H1. And similarly, playing D1 would give me this particular payoff. So H1, again, sorry for the typos here, this should be D1. H1 is going to be preferred to D1 if this particular quantity, when I play H1, gives me as good a payoff as when I play D1. So the function which I have here, the W1 function, will be sort of given by this probability. So this sort of tells me the probability that when a new agent who enters population 1, what is the probability that this particular new agent is going to play the hawkish action. Great. So these are the dynamics. And then the first thing which we show is that that's sort of a trivial thing. What we can show, since the divergence of the system is going to be negative, we can show that the system is going to converge. In particular, you can rule out complicated cycling sort of behavior. The only limiting behavior which is going to be possible is where you converge to some sort of a stationary state. And what we identify in the paper are some sufficient conditions under which the pure stationary states, or rather the pure equilibria, are going to be unstable. So I'll not like state those technical conditions. Instead, what I'll try to do is try to illustrate our results using again the phase portraits. So let's consider these diagrams. The left-hand side sort of illustrates the phase plots when I fix G and L to be 0.5 and I take a sample size of K, which is 2. So what these dynamics sort of show is that if I have a sample size of 2, eventually there is convergence to something which is in the interior. And then on the right hand side, again we have the same G and L values, but now we are increasing the value of K. If we increase the value of K, again what's going to happen is that only the boundary points are going to be stable. And the intuition for this particular thing is sort of not too hard to see. When you increase the value of K, it's sort of saying that you'll be knowing the truth more, which means that when you increase the value of K, and in the limit, if K was very, very large, if K was infinity, the best experience payoff dynamics would be qualitatively similar to the best response dynamics, because you'd kind of know everything for, you'd be sort of knowing the population state. If k was very, very large. But if k is not too large, then what this phase portrait sort of shows is that there can be convergence to something which is in the interior. And in fact, in this particular setting, when G and L are both 0.5, it's not just this particular interior state is not just asymptotically stable, but it is also globally stable. So again, I'll not get into the technical details. So let me just say that in order to assess the instability of the pure equilibria, so the standard technical procedure is that you would linearize the system around the stationary state in question, and then you would look at the eigenvalues. If even one of the eigenvalues is positive, then the state is going to be unstable. In this particular setting, the condition which sort of gives rise to instability of pure equilibria is this particular condition. So as you can see, the condition k times g being less than 1, what this is saying is that firstly, g has to be small, g has to be less than 1, and also that the sample size k has to be less than 1 by g. So intuitively, if k is very large, this will never hold, and so the boundary equilibria are going to be stable. So again, I think it's best to represent the results using phase diagrams in these sort of settings. So what these phase portraits sort of illustrate is that when you have very large values of k, as I said, the dynamics would sort of represent the best response dynamics, and the only thing which are going to be stable are sort of going to be the boundary equilibria. But interesting things sort of happen somewhere for moderate values of k. Initially, when k is just 2, there is global convergence to something which is in the interior. And then as you increase the values of k, for some values of k, both the interior states and the boundary states are both stable. And as you can see, as you go on increasing the value of k, there comes a certain stage beyond which nothing in the interior is going to be stable. So I guess that's more or less what I wanted to show. And the important theme which sort of comes in this strand of literature, which is sort of based on sampling, are these two things. So one is that non-Nash outcomes can be stable, as illustrated here. So these things do not correspond to either like the pure Nash equilibria or the mixed strategy Nash equilibria. These things can be stable, and more interestingly, strict equilibria can be unstable. And this sort of happens when the value of k is not too large. And one can rigorously show that when you increase the value of k, that strict equilibria will be stable. So these are the two themes which sort of pop out from this strand of literature. I guess this is my concluding slide. So just to sum it up, what we study are the class of Hogdorf games in the two population setting. What we show is that interior states can be stable under certain evolutionary dynamics which are based on sampling. So in particular, we consider something called as a best experience payoff dynamic, and we show that something which is in the interior can be stable. And this is in contrast to the results in the literature, which say that under many evolutionary dynamics, only the boundary points are going to be stable in the Hogdorf game. So that's the paper. And yeah, so I think coming back to this question, I hope that the question is visible to all. So this question has got nothing to do with, like the paper is still complete without proving this. So what we sort of realized is that once we plotted these functions, f of k, so here we call them w1 and w2. So what we sort of realized is that these functions are all strictly decreasing. And then we sort of conjectured that if we write down this particular function, it's probably the case that this particular function, so here what we are doing is we are fixing the values of G and L. They are some positive values. And you take some k which is an integer, and p which is between 0 and 1. Xk and ykp are IID binomial random variables with parameters k and p. And then you construct this function. So once you fix G and L, this would just sort of be a function of P, and you also have K in the subscript. So what we kind of conjectured, and we sort of think that this is true. We think that this is true, but we don't have a proof for it. So I think it will be, since this is school for theoretical sciences, I thought this would be an interesting problem to not just the students, but everyone. So I guess you can try this question, and if you succeed proving it, please do let me know. I know how to prove this in the limit, but I don't have a proof for this when k is finite. So yeah, I guess with that, I thank you all, and yeah, thanks once again to the organizers.
So, Srinivas, very nice talk. So I have a question. So have you looked at the connections of this kind of ideas with multi-armed bandit kind of problems? So in bandits also there are different arms, and we don't know the distribution of reward from each of the arms, but we pick the arms a few times and then explore and try to balance exploration with exploitation. So they are, instead of, after sampling a finite number of times, we calculate typically a confidence bound as well, and then pick the arm which has the largest empirical mean plus the confidence bound. So that kind of leads to high probability selection of the best arm. So have you
Yeah, in Spirit, these dynamics are sort of inspired by these reinforcement learning kind of things. So you don't really know the exact environment. You sort of have a brief idea. So here, the kind of idea I have as a new agent is the set of available actions. And I don't know the payoff matrix. So I just try it out a few times. So in Spirit, it is inspired by that. Yeah.
It's a scalar, right?
W is a vector. W1, W is like W1 comma W2.
Okay, so W1 is a scalar.
W1 is a scalar,
okay,
yes.
Okay.
W is a vector.
Okay, and so you are saying that you do not, the new agent who enters, she does not know the payoff matrix.
Yes.
But you are taking, so if you go to slide 15.
Yeah.
Yeah, you're saying that playing H1 gives 1 plus G times something into random variable.
Yeah, so let's say I'm the new agent. I try action H1. When the if let's say when I enter the population state is P1 comma P2. When I try out action H1, the number of hawks which I'm going to encounter will be drawn from a binomial distribution with parameters K and P2. So the number of hawks which I'm going to encounter would be xkp2. And the number of doves which I'm going to encounter is going to be k minus xkp2. So whenever I encounter a hawk, I get a payoff of 0. So I'm actually playing the game with someone and I experience a payoff. Xk times, I get a payoff of 0.
But how do you know 1 plus G? It can be something R or something.
No, so each time when, so let's say I'm a hawk player and I encounter a dove player, when I play that, I get a payoff of 1 plus G. And I'm encountering such dove players,
so you know
K
that
minus
the
X time.
structure is 1 plus something. That structure is known to you.
No. I'm just receiving a payoff of 1 plus G. So when I'm a hawk player and I encounter a dove player, I get a payoff of 1 plus G.
Okay.
So W1 plus W2 has to be 1, right? Because otherwise the simplex won't be invariant.
One second.
So in slide 8, so you have P1 dot is W1 minus P1.
P1 dot is W1 minus P1, yes.
Yeah, so the W you have written is a function from this square to this square.
Yes.
Can it be any function or should it be a
So
function?
W1 has to be between 0 and 1. W2 should also just be between 0 and 1.
Should W1 plus W2 be equal
No, not necessary.
Then there is a problem, right? Because the simplex will not be invariant anymore. Like the two simplices. Oh no, there's just one simplex.
There is, you're on a square. So the state space here, it's not a triangle. The state space, let me show, it's a square.
So P1, P2 is not a probability vector.
P1 is the fraction of agents in population 1 who are playing hawk.
It's actually on the simplex. It's on the simplex.
It's just living on this square.
Yeah, I mean it's a symplectoph. It's simplex cross simplex.
You have two lines and then you are taking the cross product of it.
So for this product to be invariant, then don't you need W1?
No. P1 plus P2 is not 1. P1 is between 0 and 1. P2 is between 0 and 1.
I have one last one maybe. So if you go to a summary, when you say certain and most, probably certain and many. So is there rather more specific classification of that?
Yeah, so many would be, so here you have sign preserving monotone dynamics under most monotone dynamics. In fact, so I like using the words almost surely and things like that because there's always a chance that it's better to say, and I guess that's the reason why when people in math write statements, especially in probability, they use almost surely and they're never sure. But yeah, here many would sort of capture most monotone dynamics, which would sort of include best response dynamics and I guess replicator and most of the commonly studied dynamics.
So when you go to certain, so here you have done payoff sampling.
Based on sampling, yes.
Right. But there could have been action sampling.
Yes.
So in that case also probably.
In that case, we have an interesting result in a different paper. What we show is that when we are considering action sampling, if everyone has the same sample size, again, only the boundary points are going to be stable. But if you have heterogeneity in sample sizes, meaning that some of the agents use small sample sizes and some of the agents use large sample sizes, something in the interior can be stable.
Any other question?
What was the motivation behind choosing these two population setting? Like what scenario could it represent?
Two population setting, like in the Hogdog game, could be like I said, buyer seller sort of a setting, or like two sort of animals being drawn from two different populations.
Right.
Yeah, that kind of a scenario.
Any others? Great. So let's close for the day then. Thanks you all. Let's thank the speaker once more as well.